Thanks everyone for coming. This is the first of our whole energy systems interest group talks by external speakers. So we're very pleased to have Thomas Morstyn with us today. He's from Edinburgh University, where he's a lecturer in power electronics and smart grids. And he's involved with a few projects there, networked market platform for electric vehicle smart charging. He's on an energy rev project in market design for scaling up local clean energy systems. And today is going to be talking about Open, which is an open source software platform for smart local energy systems. So I'm really looking forward to hearing what he has to say. And Thomas is going to give his talk, and if we could keep questions for the end. But if you have any burning questions, please write them in the chat. And if there's anything important, I'll flag it up for Thomas. And I think you've all heard a message that this presentation is being recorded. So just as a courtesy to let you know again, we are recording this message. So thanks so much, Thomas. If you can unmute and start, that would be great. Thanks.
All right, thanks very much, Chris. Thanks for inviting me, and thanks for Matt for organizing this. So today I'm going to talk about the Open Platform for Energy Networks, as was mentioned, or Open, which is an open source Python software platform for developing smart local energy system applications. And then also to illustrate the capabilities of the platform, I'll discuss a particular research project which we used it for, looking at optimization for electric vehicle smart charging, accounting for nonlinear battery voltage constraints. And this is work that I did while I was with the Energy and Power Group at the University of Oxford. And it had many contributors, including Matt Deacon, as well as Catherine Collett, Avinash Vijay, Scott Wheeler, Sivapriya Bhagavathi, Filiberto Fili, Constance Crozier, and Malcolm McCulloch. So a quick overview of the presentation. I'm going to start by discussing the potential value that localized coordination of distributed energy resources can offer. Then I'll go into discussing smart local energy systems as an important concept for organizing and managing distributed energy resources. Then I'll present a bit on the open software platform and finish off discussing the case study on conic optimization for electric vehicle smart charging, considering nonlinear battery voltage constraints. So power systems are undergoing a fundamental transition due to the rapid adoption of distributed energy resources. These include things like small and medium scale renewables, home batteries, electric vehicles, and heat pumps. And coordinating these resources to match local renewable generation with flexible demand has the potential to create value in a couple of different ways. So first, by reducing the net import and export of power in a local network, we can reduce upstream power flows, which will reduce losses. Also, this can help alleviate the need for renewable generation curtailment, which would otherwise be required due to distribution network constraints. And then if we can do this on a reliable basis, there's also the potential to defer or avoid the need for costly upstream generation, transmission, and distribution infrastructure upgrades. There's also a number of more advanced value streams that could be unlocked by coordination, such as the ability to maintain local security of supply after upstream faults, by operating the local distribution network as an autonomous microgrid, or coordinating distributed energy resources to operate in a virtual power plant so they can provide upstream flexibility services to national grid, for example. So one of the large energy initiatives in the UK is the government's Prospering from the Energy Revolution Challenge, which is a £100 million program towards the design and demonstration of smart local energy systems. And while I was with the Oxford Energy and Power Group, we were working on a number of different joint innovation projects with industry partners, which broadly fall under this category of smart local energy systems. So examples include the Vehicle to Grid Oxford project, which was developing new business models and optimization software for smart charging and vehicle to grid services from electric vehicle delivery fleets. There was the PEAT project, which was investigating a virtual power plant made up of smart electric hot water tanks, solar panels, and home batteries. And the Multi-Saves project was looking at intelligent coordination of a large book storage facility where you had solar generation and flexible HVAC. And then these projects fit within this larger project, which is still ongoing, called the Local Energy Oxfordshire project. And this was with the distribution network operator, Scottish and Southern Electricity Networks, to develop a county-wide flexibility market and data platform to help increase the hosting capacity of renewables, electric vehicles, and so on by actively managing distribution network constraints. So more broadly in the academic literature, there's a range of different strategies that have been proposed for coordinating distributed energy resources. These include things like active network management, microgrids, energy communities, multi-energy hubs, local flexibility markets, peer-to-peer trading platforms, and virtual power plants. And each of these strategies is distinct from one another, but there are also overlaps, and some of them have the potential to be combined as well. So the concept of smart local energy systems brings together these related strategies for localized coordination of distributed energy resources. And the idea is that smart local energy systems have a common set of components. So they all have a set of distributed energy resources embedded in an interconnecting local power network. They're interacting with some kind of upstream energy market, and they have a digital coordination platform providing sensing, communications, and control. And they also require a common set of management tools. So you need modeling to understand the characteristics and constraints of distributed resources in the local network. You need control to achieve system objectives within operating constraints. And you need detailed simulation to verify performance ahead of actually implementing these things. So the development of Open was motivated by a lack of adequate software tools for supporting smart local energy system research and development. In particular, the capability to model, control, and simulate distribution systems with embedded distributed resources was divided between different tools, and many of these tools lacked extensibility and interoperability, as well as more advanced modeling and control techniques. So the main aims with Open were to provide modularity and code reuse, as well as extensibility, to allow for collaboration and replication between laboratories, and then ultimately to try and speed up the translation of new methods to industry application. So a key step towards this is Open's object-oriented structure, and this allows for standardizing interfaces between components, such as resources, networks, and market arrangements, as well as different tools for modeling, control, and simulation. Also, this allows users to then expand Open's libraries of networks, market arrangements, data sets, and energy resources as they're working on their projects. And since it's developed in Python and is open source, you can easily integrate it with third-party packages such as scikit-learn for machine learning or matplotlib for visualization. So there's a large number of existing software tools for energy management, but Open offers a number of important features, particularly for smart local energy systems that are not offered by these other tools. So the existing tools can broadly be divided into three main categories. You have power network simulation tools. So these are tools focused on traditional generation, but don't consider multi-period scheduling relevant for modern systems with energy storage and flexible loads. You have energy system management tools, which focus on higher level planning, and they include multi-period scheduling, but they use simplified energy transfer network models rather than detailed electrical power flow modeling. And then the most advanced tools that are broadly offered are transmission system management tools, which address the adoption of renewable generation and energy storage by having multi-period optimal scheduling with balanced power flow models suitable for transmission systems. So some of the key differentiating features offered by Open are that it offers multi-period scheduling of distributed resources combined with detailed multi-phase distribution network modeling. So whereas balanced power flow models can be used for transmission system management, at the local distribution network, you need to account for voltage constraints and losses, as well as distributed resources being connected on different phases. Also, Open offers receding horizon scheduling and optimization, where scheduling is updated during operation based on new forecasts and a predictive system model during operation. And this is important for addressing different sources of uncertainty, as well as model approximations used for networks and resources required to reduce computational complexity for optimization. Also, Open can accommodate nonlinear energy storage modeling, which is an important feature for simulation when you want to compare different storage technology options to one another. And more broadly, this fits into the kind of fundamental structure of Open, which allows for separate model fidelities for control and simulation. And so this allows distributed resources to be scheduled based on simplified resource and network models. And then, because optimization based on a full distribution system model is sometimes considered impractical due to computational complexity or a lack of network information. And the idea is that then the suitability of this simplified control model can be rapidly prototyped by testing it with a low fidelity simulation model, and then later verified in more detail by coupling it with a higher fidelity nonlinear system model for simulation, for example. And then finally, one of the market features that Open offers, which isn't very common, is demand charges. So per kilowatt charges on the maximum demand during a particular time interval. And these are becoming more important as local energy market designs want to try and incentivize local supply demand balancing. So this slide shows a high-level UML diagram of Open, showing the platform's main classes. So Open has 4 important base classes: asset, network, market, and energy system. In Open, a smart local energy system application is built around an energy system object, which has a list of asset objects defining the loads and distributed resources. It has a network, which the asset objects are embedded within, and it has an upstream market, which the network is connected to. And so the asset class is inherited by different classes which define particular types of energy storage assets or buildings with flexible heating and other types of flexible resources you might have in your network. The network class defines the local power network and provides power flow methods for simulation. So for balanced power flow analysis suitable for the transmission system, we allow users to use the Panda Power net class from the open source Python package Panda Power. But then for unbalanced multi-phase power flow analysis, we have our own 3-phase network class, which offers nonlinear multi-phase power flow using the ZBus method. And this is similar to what's offered in OpenDSS, for example. All right, so to demonstrate the capabilities of the platform, I thought it'd be nice to instead of talking about generic case studies, look at a particular research project that we did. So our aim with this project was to develop a computationally scalable optimization strategy for electric vehicle smart charging, which could account for the limitation on the maximum charging power, which occurs at high state of charge levels when you're charging with large output powers. So the electric vehicle smart charging problem in general is the problem of coordinating when and at what power levels a group of electric vehicles should be charged at, considering network constraints on their collective charging power. So standard optimization strategies for electric vehicle smart charging are based on linear battery models, which assume that the state of charge of the battery increases linearly with charging power, and the charging power limits are not affected by the state of charge. However, in reality, these linear battery models don't account for battery voltage rise, which occurs as the state of charge of the battery increases, and this will reduce the maximum charging power of the battery. Nonlinear models can account for this, but then the optimization problem becomes non-convex, so it has exponentially increasing complexity. The effect is more prominent at higher charging powers, and therefore the challenge is particularly relevant for DC fast charging, where we have very fast charging powers relative to the size of the batteries of the vehicles. So currently DC fast charging is generally at 50 or 100 kilowatts, charging electric vehicle batteries over 30 minutes or an hour, but there's also a push towards higher charging powers, up to 400 kilowatts, so that you could charge large vehicle batteries in 5 to 15 minutes. So the figures on this slide show an example of the charging powers, state of charge levels, and voltages for a 40 kilowatt hour electric vehicle battery. As shown, when the charging power is 6.6 kilowatts, which is the kind of black dotted line, the battery can be charged at the full charging power until it's almost full. So you spend almost all of the time in this constant power kind of linear region. However, when you're charging at 50 kilowatts, which is the blue line, you can see that the charging rate has to be significantly reduced beyond around 50% charge. And so this means that the battery spends most of its time being charged in the nonlinear constant voltage region to prevent the voltage limits from being violated. And so this is a much more kind of nonlinear behavior. So nonlinear battery circuit models are often used for accurate dynamic simulations. Battery circuit models include an inner voltage source to model the open circuit voltage of the battery, and then series RC circuit elements to model the output impedance. These models incorporate the state of charge dependence of the open circuit voltage and the output impedance by making the inner voltage source and circuit elements functions of the state of charge. So as an example, what's shown here is a multi-timescale validated model for a lithium-ion battery cell used for electric vehicle applications. The open circuit voltage R and C elements are each modeled as sixth-order logarithmic polynomial functions of the state of charge. However, if we try and incorporate this model directly into an optimization problem, it's going to give us a non-convex problem, which will be very difficult to solve. So instead, what we propose was using a reduced order model, which still tries to capture the dominant dynamics associated with battery voltage rise. So we approximate the output impedance with a single fixed resistance value, and then we model the battery open circuit voltage as a linear function of stored energy. And it's worth noting that stored energy is different to state of charge, but they can be mapped numerically onto one another. So there's in some sense equivalent. Okay, so an important question then to ask is whether the reduced model is in any way a good approximation of the nonlinear model. So to compare this, we simulate the same 40 kilowatt hour battery that we were talking about before under constant power, constant voltage charging with a 50 kilowatt power limit between 10% and 100% state of charge. Over this state of charge range, the battery output impedance varies between 135 and 160 milliohms. So the assumption that resistance is fixed is not fully accurate, but it's not hugely off either. The figures compare the charging power, state of charge, and battery voltage of the two models. As shown, both models reach the constant voltage charging region at around the same time. The reduced order model slightly underpredicts the charging power after this, but overall, you can see that the two models are in reasonable agreement, with the maximum absolute error between the charging powers being less than 3 kilowatts, the errors of the state of charge levels being less than 1.5%, and the battery voltage errors being less than 3 volts. So using the reduced order model, we can formulate the maximum output voltage and maximum power limits as convex second order cone constraints. And this is how we're going to obtain this convex optimization problem. So within our optimization problem, we need to have constraints associated with the maximum output voltage of our battery and the maximum charging power. The maximum output voltage limit is imposed on the sum of the open circuit voltage and the voltage drop across the resistor, which depends on the charging power. Rearranging this relationship, we notice that the open circuit voltage is greater than 0 and that the maximum output voltage is always greater than the voltage drop across the resistor. And so this constraint can then be restated as a specific type of second order cone constraint called a hyperbolic constraint. The maximum charging power limit would also be a hyperbolic second order cone constraint with our reduced order model, except that the right-hand side of our equation has been multiplied by the open circuit voltage squared rather than just the open circuit voltage. And so what we can do is obtain a conservative approximation of this by replacing one of the open circuit voltage variables with the minimum open circuit voltage. So the inequality is kind of satisfied strictly. Okay, so now that we have the second order cone constraints, we can then formulate two different optimization problems, one with the standard linear program for electric vehicle smart charging based on the linear battery model, and the second with the same sort of structure of problem, but now with the battery voltage constraints replaced by our second order cone constraints for battery voltage and charging power. So there are a range of different electric vehicle smart charging problems that we could look at. In this particular case, we're considering that we have one or more electric vehicle charging stations embedded in a distribution network, where the objective is to charge vehicles as fast as possible, prioritizing vehicles that according to their arrival time. So each vehicle can charge while it's plugged in at the station with a particular charging power limit. And then also the charging station has a combined charging power limit that limits the sum of the charging powers of the vehicles. And we assume that the charging stations are embedded in a distribution network where there are also three-phase voltage limits. So currently, Open supports two main concepts for local energy system control: open loop control and model predictive control. So under open loop control, we calculate control references for the flexible assets in our local system based on a simplified system model and forecasts. And then we simulate what happens when these control references are applied based on a higher fidelity simulation model. But with model predictive control, scheduling proceeds with a receding time horizon, where asset control references are calculated based on a system model and forecast, but only implemented for the next energy management time step. The system is then simulated, and then the asset control references are recalculated based on the new updated system model. And so this receding time horizon control helps improve performance in cases where there's forecast error or where we're using approximate models. So for our electric vehicle charging station, we use model predictive control, where we assume that the charging station doesn't know when vehicles are going to arrive, but once a vehicle has arrived at the station, we assume that at this point it communicates its required energy as well as its planned departure time, so that the scheduling problem can be updated. So we can look at a case study to demonstrate the operation of the proposed smart charging strategy. We look at an electric vehicle charging station with DC fast charge points embedded in the IEEE 13-node test feeder, where we have 50 vehicles arriving between 6 a.m. and 6 p.m., each staying between 15 minutes and 4 hours. We assume the vehicles have battery sizes between 20 and 60 kilowatt hours, and that they're charging at 50 kilowatts. The vehicles are arriving also with state of charge levels that vary between 40% and 10%. And we assume that the charging station has an overall power limit of 120 kilowatts. So this is the maximum amount of power it can draw from the distribution network. And then we assume that the distribution network also has three-phase voltage limits of plus or minus 5%. So we formulate both of the optimization problems with a 2-hour optimization horizon and 5-minute energy management time steps. So the vehicle charging powers are being schedules are based on these sort of 5-minute time steps. And for high fidelity simulation, we simulate the battery dynamics with 6-second simulation time steps. So the results that are shown here are comparing 3 different strategies, which we look at. The first one is no coordination, where we just charge each vehicle as fast as possible once it's arrived, using constant current, constant voltage charging without considering the charging station or network constraints. The second is smart charging using the linear battery model, giving a linear optimization problem. And then the third is smart charging using the proposed battery model, which gives the second order cone program. So the figure on the left shows the total charging power of the electric vehicle station when vehicles operate under constant current, constant voltage charging without coordination, and when the vehicles are scheduled by the linear program and the proposed second order cone program. So the dotted gray line shows the constant current, constant voltage charging strategy, which gives the fastest possible charging. But since there's no coordination, the overall station charging power limit of 120 kilowatts is violated, which is expected. So as shown, both the linear program, which is the blue line, and the second order cone program, which is the kind of dashed orange line, give charging powers which do not violate the station's maximum power constraint. However, under the linear program, the optimization doesn't understand that the battery voltage limits will limit the maximum charging powers when the state of charge levels become high. So this means that it will generate unachievable control references. So this results in the overall charging station maximum power limit being underutilized. So since the second order cone program understands that vehicles with high state of charge will not be able to charge at their maximum charger rating, it's able to allocate the spare capacity to other vehicles, resulting in better utilization of the overall charging power. So then the figure on the right shows the minimum phase voltage magnitudes across the network for the three strategies. And as shown, the linear program and the second order cone program both respect the voltage limits across the three phases, even though they're both using this approximate multi-phase linear model for the network. But there's a violation of the minimum voltage limit on the B phase in the case of the constant current, constant voltage charging strategy. So the figures on this slide show the state of charge of the vehicles for the linear program and the second order cone program. The figure on the left shows the average state of charge of the vehicles over the day. As shown, the second order cone program is able to achieve a higher average state of charge by around 13%. The figure on the right shows how the final state of charge levels reached by each individual vehicle varies between the two strategies. And so you can see that almost all of the vehicles reach higher state of charge under the second order cone program, and some of them reach substantially higher state of charge. On the other hand, there are only 5 vehicles that reach a higher state of charge under the linear program, and the average difference for these vehicles is 2%. So it's a very small difference. Right, so finally, this slide, the figure on the left shows the average additional per vehicle final state of charge under the proposed second order cone program compared to the linear program for a range of alternative case studies. So in particular, we look at cases where all of the vehicles have battery sizes of either 20, 30, 40, 50, or 60 kilowatt hours, and when charging is prioritized either by vehicle arrival time or departure time. And as shown across all of these cases, the second order cone program performs better. It makes the most difference when vehicles have 30 kilowatt hour batteries. This is keeping in mind that this is quite dependent on the 50 kilowatt charging power limit that we're looking at. So when vehicles have larger batteries, the vehicles spend longer in the constant power region and less time in the constant voltage region. So this means that the difference between the linear program and the second order cone program starts to reduce. On the other hand, when the vehicles have smaller batteries, although they spend longer in the constant voltage region, the amount of energy that needs to be supplied is lower relative to the station charging power limit. And so it's less critical to have an accurate battery model in that case. So the figure on the right then looks at the computational time for the linear program and the proposed second order cone program for different problem instances with different numbers of vehicles. And you can see that the second order cone program has higher computation time as expected, and this is about an order of magnitude larger. But in both cases, the computation time is sort of sub-exponential. So this means that you can still apply the second order cone program to large problems. Right, so I wanted to finish off the presentation by discussing some of our ongoing work in the area. So Professor Cameron Hepburn and I co-lead the market design for scaling up local clean energy systems project, which is part of the multi-institution Energy Revolution Research Consortium. And on our project, we're looking at new local and system level energy market designs to support the successful scale out of smart local energy systems across the UK. And particularly on this project, we're extending open with a broader set of energy resource models, networks, and different types of local and system level market arrangements, as well as a high performance computing implementation to look at large scale simulations. And an important research direction for local energy market design, which connects to the work that I presented here, is to incorporate more detailed models of distributed energy resources as well as local distribution networks, while balancing model fidelity with computational complexity and game theoretic objectives. And this, I think, will become increasingly important as we move to a power system with a larger proportion of generation and flexibility embedded in distribution networks. And then finally, the idea is that open is open source and it's available to download and free to use. So you're very welcome to give it a try and let me know if anything breaks when you're trying to use it and so on. Thanks very much.
Thank you very much, Thomas. That was a really interesting talk. You rushed through a lot of stuff there. It sounds like you're doing a really good job with that software. I'm going to open up to questions in a minute, but I've got a few questions of my own. are you linking to a third-party optimization engine in Open, or how are you doing that?
Yes, so we've used a Python package for optimization called PyCause. So that's the main one that we're using at the moment. And that's allows for, that then can connect to different optimization solvers, such as, Cplex or MOSSEC or CVX opt. And so you can do mixed integer problems and convex problems and so on. But also the, within the energy systems class, users can define their own energy management system methods. So there's some that come with Open, which allow for these kind of different optimal power flow and copper plate optimizations and so on. But you can implement your own, and you can use other Python optimization packages if you prefer.
Wow, sounds very comprehensive.
It's sort of so what the approach that we've tried to go for is we've tried to have it as so it's not as nice in terms of the like it doesn't have at the moment a graphical user interface that allows someone to use it without Python programming knowledge.
Okay.
But the idea is that you can use it straight out of the box to do the types of sort of quite a broad set of optimal power flow, local distribution, network control, and then but it is fully open for you implementing different classes and getting into it. And hopefully it's well documented enough so that that's achievable. Yeah,
so it's a wide scope of application. That sounds good. Yeah, that was one of my questions about the graphical interface, but you just answered that.
Yeah, we haven't done that yet. We're looking for the right sort of student or postdoc to lead on that.
Yeah, sure. You're sort of covering a lot of bases with this thing, so some things will be less developed. That's perfectly understandable. Could you go back to slide 18? I think I had a question on that.
Sure. Let me see if I can figure out how to share my screen.
There should be a little arrow with a, yeah, you've got it.
All right. Slideshow
and... no, 18.
This one?
Yeah. So I think on that graph on the left, you're saying with the SOCP, you can charge more cars more quickly, kind of a thing.
Yes.
I wasn't quite sure what the right-hand side graph was saying.
Yeah. So on the right-hand side is basically showing on, I'll start with the left-hand side. You can see that you're going from, midnight to midnight. So from this 6 a.m. period when vehicles start arriving, of course, vehicles are arriving, they have low state of charge and they're being charged up. So the kind of average charge that the vehicles have, is starting at 25% and is kind of going up. Vehicles are leaving, so you can't necessarily fully charge every vehicle before it has to leave. But there's this station maximum power limit, which you're working within. And the idea is the second order cone program is able to better utilize it because it has a better understanding of how to allocate charging between the different vehicles. So that's why the second order cone program is able to reach this kind of higher level of overall state of charge. The figure on the right, the x-axis is showing the final state of charge of each vehicle under the linear program, and the y-axis is showing the final state of charge of those vehicles under the second order cone program. So in other words, for each vehicle, if it was the ones that are very close to the kind of dotted 1-to-1 line, is basically saying they get the same amount of charge in each case, right? So they're all in the top, kind of the top quadrant or the top half, what do you call that? So that's good, in other words. And the point is that this was this thing that we kind of came to when we were working on this strategy of this sort of fast charging, because often people sort of think of, oh, we have an amount, like we have to charge all the vehicles by an amount. But in this work, we were kind of looking at, well, okay, how would a fast charging station where it's trying to deliver as much energy as possible, kind of. How would it work? And so that's why we came to this thing of either prioritizing vehicles by arrival time or departure time. So they give slightly different results for individual vehicles. But the point is that in general, your, what would you say? That basically, you know, the charging station is trying to charge all of the vehicles quickly. And you wouldn't want a charging strategy that had a kind of better average performance, but then totally undercharged a couple of vehicles, because obviously those users would be very unhappy, right?
Yeah.
That's
that.
right.
Yeah, that's sort of interesting how you formulate the the optimization problem.
Yeah.
Yeah.
So there is some subtlety there. It would be like an interesting extension would be, oh, could you come up with a theoretical algorithm that kind of guaranteed that all the vehicles were at a higher charge, whereas this one, it just, in practice, it basically seems to be able to charge all of them higher, but it's not actually guaranteed.
Mm-hmm. Yeah, thanks for explaining that.
Yeah.
There's a question from Neil Wade on the chat. Great talk. Thanks, Thomas. Can you comment on how steep the learning curve is to start using open? Would someone just starting out with Python be able to get going quickly?
Yeah, I think so what we've done in the documentation and a kind of paper that goes along with open, as well as in the platform, is we've provided two kind of complete case studies. So one of them is looking at electric vehicle smart charging, but a slightly simpler problem than the one that I presented here. And the other one is looking at just a building where you have renewable, like a solar generation, flexible heating, and a time of use tariff on the building. And then, you know, it's trying to optimize the heating or cooling that we have both built into the case study. So what we've tried to do is basically have fully commented main files for each of those, which you can run. And then you can sort of see like, oh, okay, if my problem was a distribution network optimization, but I had a different distribution network or it had some different assets, I could kind of take the EV case study and then just try and like, you know, change the number of EVs to start with, or mess around with some of the parameters to get a feel of like how it works. But yeah, I mean, actually this whole experience of using open was basically part of the impetus was because I was enthusiastic about learning Python, and the team was learning Python. So it was, so I think the kind of it kind of was a learning experience doing it. So I think it's a good way for people in energy, particularly if you're familiar with MATLAB. I think you can pick it up very quickly.
Oh, thanks. Sounds good. I've got a question from Marta. Good afternoon. Thank you very much for your clear presentation. Interesting work. Do you know Power Models Distribution.jl? That's also an open source package for unbalanced distribution network optimization. Yeah, so I've had a few. So I haven't used. I guess this is in Julia. Is that right? Sorry. Is this a Julia package? I guess so. It's .jl.
Yeah. Good afternoon. Maybe I confirm it's indeed the Julia package.
Yeah. So no, I haven't. I'm not like very familiar with it, but I've had some. Let's go. Like I know that Julia is popular as a kind of alternative for Python for doing the same type of stuff, I think. There's another question in the chat, and please feel free to raise your hand in the. Is there an option to raise hand in Zoom, or just jump in? There's a question in the chat from Esan. What's the take up like? How many people are taking up open, and how would it be? How could it be rolled out to a wider audience? That's a good question. I don't know off the top of my head. I don't. It doesn't seem like from the GitHub like that many people have downloaded it yet, though it hasn't been out for too long. But mainly what we've tried to do is we kind of developed it. I showed all of the kind of broad list of authors, right, on the package and so on at the beginning, and the associated paper. And they're working on, so this is Professor Malcolm McCulloch's group, which I was with before I came over to Edinburgh, and they're working on the Local Energy Oxfordshire demonstration project, which is this kind of large smart local energy system demonstrator within the broader PFER program. So so mainly they're using it for some of the modeling work on that, and in our Energy Rev project, I'm trying to kind of market it within the to the other work packages, and we're using it within our market design work package. So we'll see, but I think it's yeah, I think it's quite. I mean, yeah, I don't have much experience with kind of marketing, different types of tools, but I think that but hopefully it fills a niche around basically having like a lot of interoperable components, as well as a lot of flexibility and the ability for people to easily extend it, rather than, whereas I think the kind of issue that we have with some of the existing tools was, you have like the times model, or you have OpenDSS or so on, but then you either have like quite difficult interfaces, or it's quite set in like what type of optimizations it can do and that kind of thing. So that was the niche we were trying to fill.
Yeah, that sounds good. Are there any more questions from our guests?
Yeah, hi, Markus.
Markus, go ahead.
Hi, Markus from TU Berlin. Yeah, thanks for the introduction. I'm definitely going to check out the tool, because we also compiled the sort of energy models in Python that we used in our projects over the time, and then it's sort of our own library now. And it's also, I think we already did a pretty good job on the object orientation we use and this sort of stuff. I think compared to your model, where we're not so good as right now the energy grid, so we haven't integrated with Panda Power yet so much. But two questions I have. One is, because while we put a lot of effort into heating, so is that something that's also on your mind? Will you like have this sort of coupling to the heating domain soon also in your models? That would be my first.
Oh yeah, do you want to ask your second question as well, or?
Okay, then the second one is when we were thinking about, okay, should we go non-linear or stay linear? We were also talking about the same project, the same problem that you motivated with that towards the end of the state of charge, you have this sort of voltage increase and you have this decrease. But then we had two thoughts which kind of kept us from doing it. So one is we saw the trend to ever getting larger batteries now, like in Tesla, Audi, e-tron, and so on. And they often hide the last percentages from the users. So the 90% that the user sees is the 100%, or this sort of stuff. And so towards the end, for example, the e-tron at 50 kilowatts will just charge towards the end completely flat. So that's actually something we saw in real data. So what's your thought about this? And the second is that actually you said it's also, okay, higher rates of charging, like let's say 150K, and this is more of a problem. But then we argued, okay, but then we don't need to do optimization so much, because we're thinking, okay, then you don't want to have this flexibility. Like if you're actually putting your money into like a supercharger, you don't want to have the controlled charging. You want to have like one car after another coming and coming and coming. So you don't actually want to do anything smart there. I mean, maybe you want to make sure that the connection point doesn't blow up. So, but then it's not optimization, then it's just simply control or something. So what's your thoughts on that?
Yeah, no, those are good questions. So the heat coupling is something which so in the paper that presents kind of open, and one of the case studies that's built into the documentation there at the moment, there is this kind of sort of simple heating model of a building that's so you can kind of see, like we're controlling temperature, and that gives you some energy flexibility. But we haven't looked at more complicated, the electricity network is coupled with a heat network or a gas grid or something like that. And that's an area which I'd like to see it expanded into. And I think that there's an opportunity there, right? Because as you're saying, like you already have, it sounds like, established libraries in Python and models and so on that interconnect. So the idea would be, hopefully you could take the network model and network models from open, and maybe even the kind of energy system structure or not, but you could take either individual classes or the kind of structure and then couple it quite easily, because all you really need from a asset model perspective is some kind of asset that can take control references as an input and can give you power injections out that can connect to, Open's network model. So what I'd like to see is, rather than us trying to build every type of resource and so on, is hopefully, other people will be like, oh, like we have interoperability, or okay, you could have the model, you could either take open models and put it in your model or so on. But I think definitely this thing of the coupling with, heat and gas networks and so on is going to be is an increasingly interesting area. In market design, I know a lot of people are working on this kind of, markets between those. The electric vehicle charging issues that you were talking about, I think those are sort of I had those thoughts when I was thinking about maybe this is why people haven't done this or whatever in the past. So the thing that convinced me to kind of do this paper were some conversations I had with people who were not, power system people, right? But they were sort of talking, when I was trying to kind of sell people on, getting an electric vehicle. And then I said, oh yeah, you charge it and, okay, maybe it takes like a couple of hours at home or, half an hour at a charging station. They were like, this look of horror on their face kind of thing. So I do think that there is a, what's called like a case for, very fast charging. And CHAdeMO and CCS, the charging standards, I know they're both looking at this kind of 400 kilowatt charging. And it seems to be that from the models that we've kind of looked at, like I was showing, I think that once you get up to around a C rate of kind of 1 or more, certainly if you have a C rate of 2, which I think is if you had 400 kilowatts, a 200 kilowatt battery is a ton for any type of electric vehicle, right? Like customer electric vehicle, then I think you still are having like a significant amount of time in this, even to get from like 50% to 80% charge, for example. The other thing I would say is then, in terms of the smart charging not being needed for the DC fast charging stations, the interesting thing with this scheduling is that it's not about scheduling the kind of the subtlety, right, with this charging station model is that it's sort of the issue comes about when you have multiple DC fast charge points at a single charging station, which you could imagine if you had many electric vehicles in the future. And then the point is that each of the individual vehicles is in fact being scheduled to charge at their maximum charging power. So it's not like you're underutilizing the ability to charge the vehicles. But the point is that the charging station as a whole probably will have a maximum charging power limit that's much less than the sum of the charging power limits of the DC fast chargers, because if they can all charge at 200 kilowatts, it would probably be a waste if you just multiplied that by 10 or 100 or whatever. So then I think there is a room for allocation. But I agree that it would have to be a sort of, okay, it's arguable, right? It would have to be
because the sort of discussions we have in this domain is, okay, I mean, the fast charger costs a ton of money. And if you put them up in a setup where you assume you have only a concurrency of, let's say, 0.1 or something, nobody would do this sort of investment. If they know just one will be charging at the same time, or 2 or 3, they will only invest into 3, 4, 5, but not into 10. So I think the sort of control charging, in my opinion, is more something in this smaller scale charging and not so much in the super fast charging, because there I want to have this sort of gas station set up, and I want to be almost able to charge all of them at the same time. And then instead maybe install like a battery or something if my control point is not so strong or something like this.
Yeah.
But I guess we will also.
Yeah, I mean, we'll see
guessing,
in practice, right?
Yeah, right.
The other thing I'd say though is in general, right? The last thing I'll add is just that the idea, right, is that because this optimization model is still convex and actually only needs a couple of parameters from the battery, it's kind of my kind of idea with it, right, is that it's quite simple and it's really not that much more computationally intensive or requires a lot more information. So it's almost in a way, it's kind of like, it doesn't cost you a lot to do this rather than a linear model. So
I mean, the model will still be also for slow charging more accurate, I guess. So I guess it's fine. Yeah. So it's I just want to, like, I don't know, just picking the
yeah. But I agree that like your things are valid, and like definitely if you were planning a DC fast charging station, you'd have to be very careful with the economics of it and stuff about like, okay, how much energy are you delivering, and like you don't want to invest in, you know, $100,000 charging points that no one's going to use or something like that.
Or that you then go down to 10 kilowatts or something, because I mean, you don't want to have like this. It's just, I don't know, our feedback we get. Yeah. Okay. Thank you.
Sure.
But great talk. Thank you.
Thanks for that question, Markus. Any more questions from anybody? That looks like a no. That was really interesting, Thomas. And I think I'm going to go and have a look at the GitHub as well, because we're doing some modeling stuff. We've started out using Calliope, you know, but it's not fixed in stone. But yeah, actually, when we were looking at which tool to use, I found the number of different tools is just overwhelming, and you know, it's quite a lot to get your head around when you're trying to choose one particular tool. Yeah, your tool Open sounds great. It sounds very broad in scope and flexible, and I hope that people do take it up and add to it and improve it. And thanks very much for coming to talk to us today.
Yeah, thank you so much for the invitation. I appreciate it.
So thanks everyone for coming, and thanks for your great questions today. And we hope to see you at the next whole energy systems talk, which off the top of my head, I'm not quite sure when it is.
It's in 2 weeks. We've got Hannah Blumfield from Reading University talking about drivers of power system stress from meteorology. She's an energy meteorologist. So, but yeah, please do come along and support that.
Thanks, Matt, for jumping in there. I was busy scrolling through my emails. Okay, thank you, everyone. And thanks very much, Thomas. And we hope to see you again. Cheerio. Bye.
Yeah.